Hi, I'm Philip Brown. I'm an assistant professor at the University of Colorado, and I'd like to talk with you about some work I've been working on for the past few years with Jason Martin, who's a professor at the University of California, Santa Barbara. So my general overarching interest is in something I call socio-technical systems, and so I'm interested in engineered infrastructure scale systems that interact with social systems, whether that mean adversaries or users or customers, in such a way that the performance of the overall system can't be blamed on one or the other of the engineered or social piece. So we find many examples of this in today's world, and we find that game theory can provide some very useful tools in analyzing and designing the interactions between these two types of systems to optimize performance of the joint system overall. So something that we find in these systems frequently is networks of interacting autonomous agents. So when we find this kind of scenario, what happens is that we would like to use game theoretic tools to design the interactions of these autonomous agents in such a way that they perform in a safe manner and they perform in an optimal manner. So the way we typically do this, the paradigm that I want to walk you through, is that we assign utility functions to each of the agents, where these utility functions are derived in some way from the system objective function. So these utility functions are aligned in some way with what we want the agents to do collectively. And then we assign each agent an algorithm of some kind, which it uses to optimize its own utility function. So there's a vast array of work that we've done on this problem where we've posed ways of choosing utility functions, we've posed ways of assigning algorithms such that this can lead to provable performance guarantees overall. And so the hope is that when the agents execute their algorithms and optimize their utility functions, that they'll jointly optimize something that we, the designer, cares about, right? They'll optimize some system objective function. But I want to focus in today on this problem of agents optimizing locally. And I want to ask, what does it actually take for the agents to do this? Well, if you look at the form of the utility function it gives each agent some valuation for their own actions, but they also they're required to know something about the actions of other agents, right? That a minus I is a non-trivial input argument to the utility function. And it turns out that most of these tools that we have for designing utility functions implicitly require connectivity with or information about the actions of many other agents. So what I want to ask today is, what can the agents do if they can't get information about agents that they need to be able to evaluate their utility functions? So you can think of this in terms of a communication link, right? If these are self-driving cars, then maybe they're actually using their onboard radios to communicate with each other and tell each other what they're doing. Or you can think of this in terms of observation. And the agents are, they're using some kind of sensing equipment to sense what each other are doing. And so in either case, if either of those pieces of equipment fails, or if something goes wrong with the communication channel, or if the weather is bad and it interferes with the proper functioning of a sensor, we want to ask, what should the agent who is denied this important information, what should that agent do to react to the problem? So our approach today is we're going to ask, can the agents locally and individually and independently choose to redesign their utility functions on the fly to respect the actual information that they have available if they can't get the information that they need? Right? So this is what we mean by a local utility redesign. We're asking, can an agent that's tasked with being part of this big optimization problem, can it change its personal local objective on the fly if it can't get information that it needs? So here's our problem setup, the basic model that we're going to be using today. I want to mention that this model isn't quite as general as we can go, and I'll point out when I get to it which pieces we can generalize. But this particular setup is a really nice one for drawing pictures and kind of walking through some problems. But it does generalize somewhat. So we have a set of n agents. We have R is our set of resources, the script R, and each agent has a set of subsets of R, which are its choices. So each agent can choose to cover any of some specified subsets of resources. Each resource has a value, VR, and then we'll write this lowercase a to denote the aggregate choice, right? So this is the the list of all the subsets that have been selected by these different agents. And so now I'm going to pose an objective that I'll call the coverage objective. So everything above here is a resource allocation problem. And now once I pose the objective function here, it'll become a coverage problem. So my question is, how can the agents select actions to maximize the total value of selected resources? Right? So we're going to take the union of all the agents' actions and then add up the value of all the actions that are contained in that union. And that's, for this talk, that's going to be our objective. But here's where we can generalize if we desire to. So all of the results in this talk generalize to the case where this W function, this system objective function, is any submodular function. This particular submodular function is the one that generates all of our worst case examples, so it's a good one to use, it's a good one to understand for benchmarking purposes, and it's also a very simple one to understand. So the question now, so notice that I have not yet defined a game, right? This is merely an optimization problem with a particular kind of product structure on the decision variable. So to turn this into a game, now the system designer who wants to solve the optimization problem needs to assign each agent a utility function. And so throughout this talk, we're going to use the marginal contribution utility function. So we're going to say each agent is going to value each of its choices based on the amount that choice contributes to the system welfare. Okay, so the functional form, the general functional form, is what you see down at the bottom. And in this particular problem, if this agent is alone and has access to 3 resources with values 5, 1, and 10, then the utilities, or the payoffs associated with those 3 actions, are 5, 1, and 10, right? If there are no other agents present, because the agent I could go to that resource with value 10 and increase the welfare of the system by 10. So of course things get more interesting if we add more agents. So now suppose there is already an agent covering that resource with a value 10. Then our agent I now no longer values that resource at 10, because now by moving to that resource with value 10, that the resource is already covered. So our agent I would not increase the value of the objective at all by moving there. So now that resource has a value of 0, and our agent would now prefer to go to the uncovered 5 resource. Okay, so that's marginal contribution, that's how it works. Now let's ask if it is a good utility function. Okay, so here's our first example game. And let's think about this game in terms of what happens if we endow the agents with a marginal contribution utility function. So notice each agent has access, all of n agents have access to that center high value resource. And then each agent also has access to its own individual low value resource. So our first question is, what's good? Well, the optimal thing for the agents to do is for one agent to go to the center and all the other agents to go to the periphery. So the second question is, does the marginal contribution utility function get us there? And let me be slightly more precise. Now let me ask, are the Nash equilibria associated with marginal contribution utility functions optimal? And so I have to gloss over this very quickly, but it turns out that this is a well-posed question. The marginal contribution utility function always generates a potential game, an exact potential game, whose potential function is equal to our system objective. And this is very easy to verify. And therefore, there are always pure Nash equilibria in this once we have the marginal contribution utility function. And so now we'll ask, does marginal contribution get us there, i.e. are the marginal contribution Nash equilibria optimal? And the answer is yes. And in fact, yes, in sort of a robust way on this example, right? Every Nash equilibrium now is optimal. In fact, any action profile where one agent is selecting the center and all the other agents are selecting the periphery is a Nash equilibrium, and it is optimal for this instance. So now we could ask, does marginal contribution solve the problem universally? And the answer is more nuanced. So here's another example. Now we can ask, what is good? Well, what's good is for the agent 1 to go left, agent 2 to go to the center to get a coverage of about 2. And now the question is, does marginal contribution get us there? And it can. You know, what you see on the slide right now is a Nash equilibrium of the marginal contribution utility functions, but so is this. And so if the agents get stuck here, which can happen, then we can end up with a suboptimal Nash equilibrium using marginal contribution utilities. But it turns out that this is the worst we can do. Okay, so there's this general fact in this class of games, and when I say this class of games, I mean the submodular class of resource allocation games. The marginal contribution utility function guarantees that every Nash equilibrium is always within 50% of optimal on that instance. So in computer science, we like to call this the price of anarchy. We like to call this relationship between the quality of a Nash equilibrium and the optimal system joint action. We like to call that the price of anarchy, which is defined in the following way. The price of anarchy is the worst case ratio, worst case over each game and then over an entire class of games, the worst case ratio between a Nash equilibrium and an optimal allocation. So in this class of games, the price of anarchy associated with marginal contribution utility functions is 1/2. And there can be a debate over whether this is a good result or a bad result, but what we're going to do today is treat this as the baseline. So we're going to treat this as our benchmark result, whether it's good or bad. And if you wanted to think of it as good, what it means is that a Nash equilibrium can never be worse than twice as bad or half as good as an optimal allocation, right? Which is yeah, I mean, that's at least encouraging to know that there's a bound on the inefficiency of these equilibria. All right, in any case, this is our benchmark. This is what's achievable when every agent can see every other agent. So now let's ask what happens if agents cannot see other agents. So our very simple starter question that's really easy to illustrate with pictures is, what if one agent is blind? So now let's separate our agents into two different classes. One of them is the nominal class, which can see all the choices of the other agents and can see the resource values, and then goes and maximizes its marginal contribution utility as usual. The other class is the blind class. So a blind agent now cannot see the choices of other agents, but can still see the values of the resources. So it does have some information about what's good to do. It just has no information about what other agents are doing. And so the behavior of this blind agent is going to be to select the highest value resource that it has access to. Essentially what it's doing, right, its new utility function that it has now adopted implicitly is the marginal contribution to the empty set. So the blind agent is going to essentially assume that it is alone in the game. So the question is, how much harm can this blindness cause? That's our starter question, and then we're going to generalize from there. So we can look at our first example and ask that question and notice that here the blind agent will always go directly to the center, right? The blind agent it'll always just pick the largest value that it has access to, which is by a very long shot, it's the center resource. So then these periphery agents, they all go to the periphery resources, and the price of anarchy on this instance is still 1. So the presence of a blind agent changes nothing. Except that now there's only one Nash equilibrium instead of multiple. However, on this example, the blind agent will always choose the center for any positive epsilon, and then the second agent will always choose that very low value resource on the right, and so the price of anarchy of this instance degrades to 1/2. So this is an example of a case where now there isn't a good equilibrium, whereas there had been when the agent could see, but at least the presence of the blind agent hasn't made anything worse than the worst it could be when every agent could see. So our observation here could be, our conjecture could be, that blind agents don't change the price of anarchy. I should say one blind agent doesn't change the price of anarchy. Okay. And it turns out this is the case, and we're going to show this a little bit more formally in a minute using some other tools. But first, I want to ask, how do we generalize this concept? How do we take this idea that a blind agent can't hurt anything and generalize this to something more interesting? So what we're going to do is we're going to describe the graph of which agents cannot see which other agents with this object called the disconnection graph. And so this is absolutely a negative graph. So you need to be thinking about an edge in this graph as a bad thing. So essentially an edge in this graph, a directed edge from node I or from agent I to agent J, means that agent I can't see the action choice of agent J. In other words, agent I's utility function is constrained to be constant in the action choice of agent J. Okay, so for example, if agent 1 is blind, then this is the resulting disconnection graph that models that scenario. So agent 1 cannot see agent 2, and agent 1 cannot see agent 3, and that's denoted by the edges that exist from 1 to 2 and 1 to 3, but agent 2 and 3 can see everything. Okay, so edges in this disconnection graph are bad, right? They indicate a directed blindness. So if that's the disconnection graph, now what I want to quantify on this graph is something called the size of the minimum feedback vertex set. So if you're a graph theory person, maybe you understood that, but for all of us normal people, let me tell you what that means. What I want to do is I want to ask, what is the smallest number of agents which I can remove from this graph, along with their associated edges, to render the graph acyclic? Okay, so I'm trying to search the graph for agents to remove such that the graph will be acyclic, and I want to remove the fewest number of agents possible. So this M of D quantity is the smallest number of agents I can remove, which renders D acyclic, and this is going to be the driver of our price of anarchy guarantees in this paper. So here on this particular graph, M of D is 0, right? The graph is already acyclic. There are no directed cycles in this disconnection graph. And so here the disconnection factor, or the M of D, is just equal to 0. In this graph, on the other hand, there is a directed cycle from 1 to 2 back to 1. And so M of D is 1, right? If I remove either agent 1 or agent 2, that renders the graph acyclic, so we end up with that being the size of our minimum feedback vertex set. So here's our main theorem. So let D be the disconnection graph for a distributed resource coverage game, as I've described. Then the price of anarchy satisfies the following. It's 1 divided by 2 plus M of D, right? So if M of D is 0, then our price of anarchy is unchanged from the nominal case. But then as M of D increases, then we end up with the price of anarchy degrading gracefully. And so let's just put this in context a little bit. So for example, this disconnection graph has an M of D of 0 because it is acyclic. And so that means regardless of how the resources are set up and how the action sets are set up between the different agents, the price of anarchy of this graph is at least 1/2, right? Without knowing anything about the resources or even the objective function of this problem, other than that it's submodular, I know that any Nash equilibrium for this game is at least as good as 50% of optimal. All right, so I can add one more edge to this disconnection graph and get the following, and now my M of D is 1. Right? There's a directed cycle between 1 and 2, so removing either 1 or 2 makes the graph acyclic. And here now the price of anarchy is at least 1/3 because M of D is 1, and so that means regardless of what's happening in the rest of the world, and regardless of the resource values and the action sets and all that sort of thing, the Nash equilibrium is at least as good as 1/3 of optimal on this graph. Okay. So a couple other points. This proves the conjecture we made earlier that a single blind agent causes no harm. So the observation we made based on the example problems was correct. And also it shows us that the disconnection graph can contain quadratically many edges, in fact almost half the total number of edges in a complete graph, without harming the price of anarchy. And you can work through this yourself by realizing that a directed graph can contain, think about a complete DAG, directed acyclic graph, can contain almost half the total possible edges in a complete directed graph, which is quadratically many edges. And so this gives a sense of strong apparent robustness, right? It appears that only losing a few edges can't cause all that much harm, and the harm that is caused in terms of performance guarantees it degrades what we would call gracefully in the number of edges that we are losing. So now we want to ask, what about general games? And what we'll do is we'll relax submodularity. So we have to pause slightly here and say, if we just relax submodularity, then it is trivially easy to make arbitrarily fragile games. So we need more than merely relaxing submodularity. And I'm just going to skip ahead, give you the spoiler here and say it turns out that that we can make fragile games no matter what we do, as long as we relax submodularity. So now what I'm going to do is set myself up for a strong negative result. So a strong negative result is established when you make many favorable assumptions, and then even under favorable assumptions can derive the negative result. So here what I'm going to do is I'm going to relax submodularity, but then in return I'm going to require that all of the games under consideration are potential games with unique good equilibria. And when I say good equilibria, what I mean is that the objective function will just be equal to the potential function. So, and if the equilibria in a potential game are unique, then any reasonable agent learning process will allow the agents to find the equilibrium. I'm going to ask that the disconnection graph has a single directed edge, and so without loss of generality, we'll just say agent 1 cannot see the action choice of agent 2. And furthermore, agent 2 will be almost irrelevant to agent 1's utility function. So you can think of this, if agent 1 is the row agent in a matrix game, you can think of this as meaning that the rows of agent 1's utility function are flat, nearly flat. If agent 2 changes its action, then this barely changes the payoff to agent 1. Right? Agent 2 has almost no control over the payoff of agent 1. And so then what we're going to ask is under this scenario, is there a robust way that agent 1 can select itself a new utility function that preserves the good behavior? Right? We begin with perfect behavior. We begin with a very well-behaved game. We remove one of the observation edges in the graph. So now our disconnection graph has a single edge in it. And then we ask, can agent 1 recover from this problem in some robust way? Turns out the answer is no. And so let me briefly walk through why. So this is our game. This is reproduced in our papers online, so you're welcome to reach out to me and I can point you to this. But on the left, you have agent 1's utility function. On the right, you have agent 2's utility function. And agent 2's utility function is also going to be equal to the system objective function and also equal to the potential function. Okay, so the matrix on the right is playing triple duty. There's three things going on there. So note that the maximum potential value there is in the upper left. And so that's our model of what we want to happen as a system designer. And since it's a potential game, and you can verify that it's a potential game, this is selected by the agents almost surely as time goes on under any reasonable update process. Notice also that player 2 has a weakly dominant strategy to play the left action. So to play that action, which would eventually yield the optimal action profile. So now what if player 1 cannot observe the action choice of player 2? So nominally, if player 1 can see what player 2 is doing, then player 1 just selects between a pair of numbers and picks the bigger number to choose which action to do. However, if player 1 can't see the choice of player 2, then player 1 has to select between two sets of numbers. And I've reproduced and reordered the sets above this payoff matrix, so where it says up and down right there above the payoff matrix. And notice that there is no reasonable choice that player 1 has to go up. Anything player 1 does with those two sets of numbers would indicate to it that it should go down. If player 1 asks, what's the maximum payoff? Then it would go down. If player 1 asks, what's the minimum payoff? Then it would go down. The same goes for median. The same goes for mean. The same goes for anything that combines all these different things. For example, if I said, what's the median of the top K actions, or the top K payoffs, you'd still end up with the choice to go down. In this scenario. So player 1 goes down, and now what that does is it yields a new Nash equilibrium, a new unique Nash equilibrium that's worse than optimal. So if there's just these two players, this is as bad as we can get, but if we add a third player, then this new unique equilibrium can be arbitrarily bad. And the full details are extremely difficult to walk through, but you can read them in our paper. Essentially what happens is you have players 1 and 2 get us to this point, and then you have a third player that you can picture would take us up one level, increasing the potential just slightly, but less than by less than 2 epsilon. And then the process would repeat on that level, and then the third player would take us up another level, process would repeat. And you can do this as many times as you want and get the potential value down as low as you would like it to go. So you can do this to take a potential game with a unique good equilibrium and these arbitrary and these flat payoff rows, and change it, right? Have player 1 not be able to see player 2 in such a way that now the unique Nash equilibrium of the modified game is as low, has as low an objective value or potential value as you would like. So in other words, if we relax submodularity, we end up with arbitrary fragility, and it doesn't seem possible for the agent, for the denied agent, to be able to update its utility function using only its local information. So that's the summary that I wanted to give you today. Of course, reach out to me if you're interested in collaborating or if you want preprints of various versions of the paper. There are a few floating around online. But what I want to leave you with is that if we enforce submodularity in resource allocation games, then we have a strong notion of robustness. And this actually appears in many different contexts, and we have a bunch of ongoing work in this area. In other words, local utility redesign appears feasible with submodular games. However, if we relax submodularity, even if we enforce a bunch of highly favorable assumptions, then we end up with a high degree of fragility where a single lost observation edge can cause arbitrarily poor behavior. In other words, if we don't have submodularity and we're worried about having some kind of observation failures, then we may need to go redesign the agent utility functions in some kind of centralized global way. So thank you very much. I look forward to your questions and your comments. And last, I want to thank my sponsors at the U.S. National Science Foundation for supporting this work.